All right, so we have derived a theory for series circuit and the parallel circuit of resistors last time. Actually, there's a way to test this theory, okay? So that's what we're gonna do now, and we are gonna do this experiment here. I'm gonna do this experiment here. You can see we can verify these two theories, okay? Take a look at the question on slide 8, okay? If a light bulb is connected to a battery and another identical light bulb is also connected to the battery and in series with the first light bulb, so the first light bulb will get brighter, dimmer, or no change in brightness. So what does that mean? So if I have the simplest case, right? This is light bulb, I connect it to a battery. Now, if I have the same battery, now I'm going to make a different circuit, but with the same two identical light bulbs to the original battery. So I want to compare the brightness of this original light bulb, right? So this guy, let's call it R1. R1. Okay, so this is R2, but R1 and R2, they're identical, so they're equal, okay? So how does the brightness of this light bulb change? What determines the brightness of a light bulb? The power, right? If you have bought like light bulbs from a market, right? You know that the bulb with a higher power is gonna get brighter, okay? When it's connected to the same voltage source. So basically, the problem just wants you to figure out how the power changes, okay, if you connect another identical resistor or light bulb to the original one in the same circuit, okay? So that means you just want to figure out this P1, how does this P1 change, okay? So how do I compare, let's call this P1 prime. How do we compare the power? How do I figure out the power, how the power changes? Again, we don't do things intuitively, okay? Don't always use some simple logic. Use words to figure out the final answer, okay? Sometimes you may get the right answer, okay? But sometimes you don't, okay? You do math, okay? We do math. So all I need to do is just figure out this guy is going to get larger or smaller or no change when I make this change, okay? Then how do I find that? What determines power of a resistor in a circuit? We learned that. I times V, right? So that's how I'm going to figure that out mathematically, okay? All I need to figure out is that, take a look at this R1. In these two circuits, how does the current change? How does the voltage change, okay? If I connected this R1 and these two different circuits. So I can compare, if I can compare this I1 with this I1 prime, and then V1 with this V1 prime, then I know how the power changes, right? For example, if both of these two guys are smaller than these two guys, okay, the power is gonna go down in this circuit. If both of them go up, okay, that means the power is gonna go up, it's gonna get brighter in this circuit, okay? Now let's see. Then you're gonna use the theory for the series circuit, okay? In this case, V1 is definitely just gonna be V total, right? So V1 equals V total in this case. Now, what about I1? I1 is going to be V1 over R1, right? So it's just going to be V total over R1, okay? And then if you multiply them together, what do you get? You will get, so P1 is going to equal to V total squared over R1. I don't have numbers, that's fine. I just want to see how these values are going to change if I switch to this circuit. Now let's take a look at this circuit. So I want to find this I1 prime and V1 prime. In this case, I know that if they are connected in series, I would have V1 prime plus V2 equals V total for sure, right? So then V1 prime, because none of them is going to be equal to V total, because they only get part of the voltage from the battery, right? So this is going to be equal to this minus V2. No, we don't do near that. Okay, let's do this. And because they are identical, they are definitely identical. In this case, they will get the same voltage, right? So V1 prime is going to definitely be equal to V2 in this case, okay? If they are equal, okay, so that means V1 prime is going to become half of the voltage. Okay? So, and then what about I1 prime? I1 prime, it's going to be V1 prime over R1. So it's going to be 1/2 V total divided by R1. Now multiply them together. What is P1 prime? It's going to be I1 prime times V1 prime. Okay, you multiply them together, you get 1/4, because this is 1/2 V times 1/2 V over R. Now compare with P1 prime and P1. Of course, this guy is going to be smaller. So if you connect them this way, you connect two of them together compared to the original circuit, the same light bulb is going to get dimmer. Okay? So that's our conclusion. So this is going to be general conclusion. If the original circuit only has one light bulb, and then you connect another one. So it doesn't have to be identical actually, right? You connected another light bulb to the first light bulb, and then in series in the same circuit. This guy is going to always take some of the voltage away, right? Initially, this guy gets all the voltage, right? Like say 10 volts. But if you connect another one to the original one in series, it's going to definitely take some voltage away, right? Doesn't matter how small that is, right? Say if this guy takes 1 volt away, this guy still have 9 volts left. That's fine, right? The voltage goes down for this guy because initially it gets 10 volts, now it gets 9 volts. Voltage goes down, the current on this guy is going to definitely go down, right? Because the current is always voltage divided by resistance, right? And resistance doesn't change. So voltage goes down, current goes down, so the power on this guy is definitely going to be smaller than the original circuit, right? So always true. So they don't even need to be identical, okay? If you connect another light bulb to the original light bulb, it will make the original light bulb dimmer, okay? For sure. So that's our answer in this part. Now, what about the second part, okay? If I connect another light bulb in parallel with the first light bulb, okay? So how does the power change? Now let's draw another circuit. So I still have the R1 here. Now I'm going to connect another R2 in parallel to it. So I still want to compare this with this, the original one, right? How does the brightness change, right? Again, you just need to find out how the power changes. How do I figure out how the power changes? Power always equals voltage over resistance, okay? In this case, this R1 is going to get total voltage, 10 volts, say. Now, what about this guy? If this is still 10 volts, right? What is the voltage this R1 gets if you connect another one, R2, to it, okay? Identical, or it doesn't really matter if it's identical. It will still get the total voltage, 10 volts. Because they are in parallel. They are both connected to the same 2 points and then directly to the battery, right? So you see that V1 doesn't change if you compare this circuit and this circuit. Then what about I1? I1 is not going to change either, right? Because I1 is going to be equal to V1 over R1. If the V doesn't change, then I doesn't change. If V and I don't change. But that means the power doesn't change, right? Because the power is always going to be I1, V1. So if you compare this circuit and this circuit, you only look at this R1. The R1 is going to get the same voltage, the same current, so the power is going to be the same. So the brightness is not going to change, okay? So that means if you connect another light bulb to it, you see that it doesn't have to be equal to that, okay? The brightness is going to be the same because the power doesn't change, right? So, and then you can generalize it. Even if you connect 3 of them, 4 of them together, the brightness of this guy is going to be identical, the same as if this guy is connected to the battery only itself, okay? So we can do this experiment here as a test, right? That's how we test a theory, right? You make a, you set up an experiment, you can test the theory. So our theory is this. If I have some light bulbs, right? If I connect one of them to this voltage source, and then I compare it to the light bulb, a few light bulbs in series. So the first light bulb is going to get dimmer, always, right? Because some other light bulbs, they're going to take away some voltage. If I connect all of them in parallel, so the brightness is not going to change, right? The other light bulbs you connected to the original circuit don't really affect the first light bulb. So let's do that. So now I have a bunch of light bulbs here. Hope you can see them. I have 4 of them. The first thing I'm going to do is I'm going to connect this one to the voltage source and see how bright it is. Okay. So the voltage source is here. I'm going to turn it on. See, it's very bright. I hope you can see that. Okay, in the video. Okay. Now what I'm going to do, I'm going to test this parallel first. Parallel is easy to connect, okay? So I'm going to connect all these 3 guys in parallel to this light bulb and see how the brightness changes, okay? So let's do that. So I'm going to connect this guy parallel to it, okay? So that's the second one I connected to it. The brightness of this guy doesn't change, right? Because they're totally independent. They don't depend on each other. And then I can even connect a third guy. Hope you can see them, okay, in the video, okay. And then I connect the third guy. The brightness doesn't change. Not the total brightness. Total brightness definitely get brighter, right? Because now you have like 3 of them. But the brightness of the first one never changes, right? Still going to be the same. And I can even connect the 4th one to the circuit, and then the brightness of this first one doesn't change at all. Okay, so I hope you can see them. Okay, now, so we have confirmed this. Okay, now I'm gonna do the series. Okay, so remember, this is how bright this one single light bulb is. If I connect all of them in series, they're going to become really dim, okay? So I'm going to disconnect it. I'm going to connect everything in series, okay? To see how dim it's going to get. Now I've connected them in. You see, can you see that? It's really dim now because I have 4 of them connected. Okay, I don't know if you can see them. Okay, what about we try 3? So it's not going to be that dim. Now that's 2, right? That's going to be dimmer than 1 connected together. Okay, if we try 3. Then it's going to be even dimmer. Okay, that's 3. Hope you can see that. And then if we connect 4, that's going to be even worse. Okay. That's series. Okay? All right? So we have confirmed these theories. These theories, they're true. They're not like theories made up by physicists. Okay. All right, so we have done that. So now, okay, the next thing I want to do is this. So as we're dealing with capacitors, when you have a very complicated circuit, You don't only have these capacitor resistors in parallel or a lot of them in series, right? You may have like them in parallel here and series there. How do you simplify a circuit to find equivalent resistance and the voltage or current on a single one? Okay, so that's what we want to do now. So let's see. Take a look at the circuit on slide 10. So that's a circuit we want to simplify. Okay, erase this. Now I want to find the current through the battery, right? So let's first draw it. I'm going to draw it out. So this is 12 volts. There are 4 of them. And then there's one here. There's one here. Okay, and we have numbers here. This is 600 ohms, 400 ohms. This is a 560 ohms, and this is 800 ohms. So we want to find the current through the battery. So we want to find actually the total current, right? If you look at the original diagram, you don't know how to manipulate these numbers to find the current, right? Because this is really complicated, right? The current starts from here, then it's going to split, and then to all these branches, it's going to come back at the end. I know, but how do I use this, manipulate these numbers I get from the problem to find this? I don't know, right? But if I can simplify this diagram to a diagram like this, if I'm able to simplify this diagram to the simplest diagram I can get, and then I can find this REQ of this whole circuit, well, the current is very easy, right? I total is just going to be 12 volts over this REQ, because that's the simplest circuit you can get, right? And this guy is just going to get all the voltage, all the current. So my goal is this. I want to find REQ, the equivalent resistance of these 4 guys. Again, we're going to do that in steps. Don't do everything in one step. Don't do everything on this original diagram. It's very likely you're going to make a mistake, okay? So as we did with the capacitors, we're going to draw all these intermediate diagrams to help us, okay? So first of all, I'm going to identify some very small combination that's definitely parallel or series 100%. I'm going to start from there, right? I don't know how to combine these 4 numbers to get the REQ. That's fine. Let's start with something small, okay? Take a look at these 2 guys here, 600 and 400, right? Can you see that they are in parallel series? They are in parallel, right? Why? Because they are connected to the same 2 points, right? So they are definitely in parallel. So I don't know what to do with these guys, but at least I can replace these 2 guys with their equivalent. That's going to be the first diagram I draw, okay? So I still have, don't do everything in one step. So this is the first diagram, and I'm going to call this REQ1. So, and then this 560 is still there, and then this 800 is still there. Now you see that you can definitely find REQ1, right? Because they are in parallel, we're just going to use the parallel theory, 1 over REQ1 equals 1 over 600 plus 1 over 400, right? That's the theory for parallel circuit. And then you can find a number. Then you start from there. I still don't know what to do with these 3 numbers. Can you find 2 or 3, 2 of them in parallel and series? Okay, for sure, 100%. These 2 guys. right? I don't care what this guy's connected, what this guy's connected. If I take a look at these two guys, one after the other, there's only one path connecting them. The path doesn't split, right? There's an angle here, that's fine, right? That's a diagram, right? You don't need to draw an angle, right, if you like, okay? You don't need to draw a right angle, right, okay? So, but what about this guy? You don't know, actually. Are they in parallel series with this guy? You're not sure, so don't do that. Start with these two guys, okay? That's gonna be the next diagram I draw. So I'm gonna still have the battery here. I'm gonna still have this 800 here. Now I'm gonna replace these two guys with one. Again, it doesn't matter where you draw. You can draw it here or here, right? These diagrams, they're schematics. They're not going to change the physics, okay, how you draw that. So let's call this REQ2. So first of all, how do I find REQ2? Well, that's easy. They're in series. I'm going to add them together. So that's how I find this number. Now you see that you can combine these two guys. They are definitely in parallel because they are both connected to the same 2 points, okay? So even if you draw this REQ here, they're still connected to the same 2 points. Or you can draw this REQ here, right? It doesn't matter where you draw it, how you draw it, okay? The relation between them is not going to change. Now they are in parallel, so at the end, that's going to be the final REQ, and then this final REQ, how do you find it? It's going to be 1 over 800 plus 1 over this REQ2. That's going to help me find the final equivalent. And once I have the final equivalent, go ahead and use Ohm's law, because this diagram is going to be the equivalent to the first one, the original one. That's why we call it equivalent, okay? Then you can go ahead and find the current. That's always how we solve a complicated circuit. All right, so now you can pause the video and then do the algebra. Okay? All right, so now let's see. If you combine these two guys, you do this algebra, you get 240 ohms, right? So this guy is 240 ohms. Now you combine these two guys, you just add them because they are in series. So that's going to be 800 ohms. So, oh, this guy is also 800 ohms. Nice. Now the final step, you combine these two guys in parallel. What is REQ? REQ you get, the final REQ is going to be 400 ohms. Okay. And then you go ahead, use Ohm's law and this simplest diagram, right? You divide them, you're just going to get 0.03 amps. Okay? So that's how we find the REQ for this whole circuit. Okay? Then we can find the current through the battery. Okay? Okay, so now the second part of this question. Find the current through the 400 ohm resistor. So we want to find the current of this guy, through this guy, right? Well, again, if you use the original diagram, you don't know how to manipulate these numbers to find the current through this 400 ohm resistor. So like what we did with the capacitors, you're going to use these diagrams to go backwards, okay? That's the reason we draw these diagrams. It's going to help you to figure out everything on each element on this original diagram, okay? So always draw this diagram if you want to simplify the circuit and then find the information of a single element on the original diagram. So how do we use this diagram to go backwards? Take a look at this one. This diagram, we already know everything, right? Voltage, 12 volts. The resistance, we found 400 ohms. Current, 0.03 amps. We know everything in this diagram. We're good with this diagram. But this is not the problem asking us to find, right? So let's go back to this diagram. Then we can find everything on this diagram. So let's see. The voltage is 12 volts. Now these two guys, obviously they are in parallel. And we figured that out, right? That's how we got this total REQ. So that means each of them is going to get 12 volts from the battery because they are in parallel and directly connected to the battery. So this guy is going to have 12 volts. This guy is going to also have 12 volts. Now you see that once I have the voltage and ohm resistance of this guy, I can definitely find the current on this guy, right? That's going to be just the voltage over the resistance. So I can find this value, okay? And then what about this guy? Well, you can also do that. The current of this guy is going to be the voltage divided by the resistance. So that's going to be the current. Now you see that for this diagram, you already know everything you need, right? Voltage, resistance, current for this resistor. Voltage, resistance, current for this resistor. You know everything on this diagram, okay? But again, this is not something the problem asks us to find. Doesn't matter. Let's go back one more step. Let's take a look at this diagram, okay? So once you have figured out everything in this diagram, you can use the information to help you figure out everything on this diagram, okay? Maybe you don't need them, okay? Need everything to figure out what the problem is asking you for, but that's our strategy, okay? This guy is 800, so there's no difference. So you already found everything for this 800 ohm resistor in this side, so you don't need to worry about that. But these two guys are new, right? So I can use information in this diagram to figure out everything for this 240 ohm, this REQ1, and this 560. How do I do that? Let's take a look at them. What's the connection between them? The connection between them is this, right? We replaced these two guys with their equivalent, right? And then we figure they're in series, so we replace that with the equivalent and we added them together to get the equivalent. So if they are in series, they must have the same current as well as their equivalent, right? So that's the theory we figure. So whatever this current I found here, that's going to be the same current this guy carries. So IEQ1 is going to be that number I found on this diagram, right? And then this I560 is going to also be equal to IEQ2, right? So now you see that I know the resistance, I know the current, right, which is going to be this number. Then I should be able to find the voltage on this guy, right, which is just going to be IEQ1 times REQ1. Because I know these two numbers, I multiply them together. So now I have found everything for this resistor. Resistance, current, voltage. You can do the same thing with this 560. Resistance, current. Now what about the voltage? Well, if you want to find the voltage, go ahead. Just do I560 times 560 ohms, right? Because that's the resistance. Everything for this guy, you already found them. Resistance, current, voltage. You know everything in this diagram, including this guy, right? But again, this is not something we need to find, right? The problem doesn't say find anything for this 800 ohm, or something for this 560, or something for this REQ1. No, that's fine. Let's go backwards to the original one. Now you see that I see this 400 ohm resistor, so pretty much in principle I can find everything on this diagram. So that's going to just give me any information I need for this 400 ohm resistor. So now let's see, you're going to use the numbers you find in this diagram and then find all the information you need in this original. What's the connection between this diagram and that diagram? The connection is this. We figured these two guys are in parallel, so we replace them with their equivalent 240, right? So that's the only difference between these two diagrams. That's the connection between them. Because they are in parallel, they must have the same voltage, right? That's the theory for parallel. They must have the same voltage as well as their equivalent, right? So whatever this is their equivalent, this voltage is going to be the same as this voltage and this voltage. So if I want the voltage on this 600 ohm resistor, that's going to be the voltage I found here. And if I want the voltage on this 400 resistor, that's going to be also the same voltage because they are in parallel. They must have the same voltage as well as their equivalent. Now you see that once I have this voltage, I can go ahead, find the current on this 400 ohm resistor. That's going to be my answer to the question, right? Of course, I can also find the current through this 600 ohm resistor, and then I know everything on this original diagram. That's how we use all these diagrams to figure out anything on a single element, right? On the original diagram. You always use these diagrams, okay? All right, so now you can pause the video, use these diagrams to go backwards until you find this number, okay? Now let's see. The first number I need is going to be this IEQ2, right? So this IEQ2 is going to be this divided by that. So it's going to be 12 divided by 800, okay? So that's going to be 0.015 amps, okay? I can also calculate that. This is also, but I don't need that actually. So, but this is going to be the same, okay? So if the problem says find the current through this 800 ohm resistor, I would stop here, right? That's going to be my answer, okay? Now I'm going to use this to find this voltage, right? Because I'm going to need this voltage in that diagram. So then you see that because this current is the same as IEQ2, so you multiply these two numbers together, you should get the voltage on this guy. That's going to be 3.6 volts. Okay, of course you can multiply these two numbers to get the voltage on this 560 ohm resistor if you want, or if the problem asks you. Okay, then you know all the information on this diagram, and then I'm gonna use this number because this number is gonna be a 3.6 volt. The voltage on this 400 ohm resistor, also the voltage for this 600 ohm resistor. Now you go ahead, plug that in. You will get the current through this 400 ohm resistor, okay? So that's how we always draw these diagrams. You draw these diagrams, everything is clear. You're not going to make any mistake, okay? You can always find the equivalent, total equivalent resistance of this diagram. You can also find anything you need on this original diagram, okay? All right, so I've finished that. So the next thing we want to discuss is the fuses and circuit breakers, okay? Because they're very important in household circuits, so we want to take a look at it. And I also want to show you a very nice demo here, so that's why we want to discuss this, okay? So, and we actually discussed the short circuit, right, at the very beginning of this part. And short circuits, they're very dangerous. They can damage everything in this circuit. So in real life, we use fuses, okay, to prevent overloading in electric circuits, right? So the idea is this, okay, the fuse, okay, is usually a very thin metal, okay, and this metal is just gonna break. It's gonna when it gets hot, right? Because when the current gets large, then the metal is going to get hot. So this fuse strip, take a look at the fuses, the real fuses on slide 13. They're going to melt very soon when the current gets too high. It gets too hot, okay? And then once they break, it's going to open the whole circuit. So there's no current in this circuit anymore, so it prevents the large current to damage any element in this circuit. Right. So in this case, you're going to make sure the circuit is in series or parallel with the load. Remember the theory we learned about the series and parallel. You want this fuse, when it breaks, you want this fuse to open the whole circuit. Right? The whole circuit should break down. The whole circuit should fail. No current at all. You're going to make sure the fuse is in series with them. Right? If you put the fuse in parallel with them, the fuse breaks, but the other guys, the other elements, they're still connected to the voltage source. So it's not protecting these loads, okay? So that's what a fuse does, okay? And then there's a better version to protect the circuit from overloading, that's the circuit breaker. Okay, I think you have seen this box in your home. Okay, when you open that, you see a lot of switches. Okay, their circuit. This is the circuit breaker. And then the idea of the circuit breaker. Take a look at the image on slide 14. It's very nice. Okay, it has a bimetallic strip. Okay, so which is made of two different metals. Okay, and these two different metals, they're gonna expand differently. Okay, they're gonna expand at different rates when they're heated. Okay, so when the current gets too high, they get really hot, they get warm, and then so their expansion is different. Okay, so they're not gonna become straight. Okay, so they're not gonna stay flat. The strip is going to bend one way depending on which one has a larger expansion, right? So take a look at the image at the bottom, okay? So you see that if it expands, it bends to the right, so it's going to push the latch, and then it's going to open the circuit, right? So the circuit is going to open, so no current is going to go through to the load, so it's going to protect the load from overloading from a very large current. Okay, and in this case, you don't need to replace the fuse, right? Because when the fuse is always a very, very thin metal inside the fuse. So once it melts, you're going to replace it with a new one, right? So the advantage of a circuit breaker is that it can be replaced, right? It can be reset. You don't need to replace anything, right? All you need to do, if it opens, you first of all, you need to figure out. You need to do some tests to figure out where went wrong in this whole circuit. And then once you fix that, you can just put the breaker back on, okay, to resume the normal operation. So it's much nicer than the fuse, okay? So that's why it's widely used in households, okay? So again, if you want to make sure that the circuit breaker protects the loads in your house, you're going to still make sure the circuit breaker is in series with the load, right? It's not in parallel, because when it's in parallel, then it doesn't really open the whole circuit, right? It breaks it itself, right? All the other elements, they're still connected to the source, all right? So I do have a very nice demo for the fuse here. Eric Chapman set this up for me. So we can see how the fuse is going to protect the circuit, okay, when the current goes too high, okay. So I do have a few light bulbs here. I have five of them, okay, and then they are connected in parallel. So these guys, they are connected in parallel, but this combination is connected in series with this very, very thin fuse, this very, very thin metal. Okay, maybe you can see that because this is very, very thin. Okay, so if what I'm gonna do is I'm gonna connect these light bulbs one by one to the circuit. Okay, and then remember these five guys, they are in parallel. So if you connect more and more light bulbs in parallel with each other, the total current in this circuit is going to go up, right? We learned that in the parallel circuit, the total current is going to be equal to the sum of all these currents, right? And each current is only going to be determined by the voltage, right? So this is what happens, okay? And then this is the fuse. So I have all these light bulbs here. This is the fuse, okay? So the total current, if the fuse is good, the total current is always going to be equal to I1 plus I2 plus I3 plus I4 dot dot, right? In this case. So if I connect more and more light bulbs to the circuit, I get larger and larger current, right? The total current through the fuse, right? Remember the fuse is connected to in series with this load. If you replace these four guys with one guy, you have a fuse and then another equivalent, okay? So when I connect more and more light bulbs to the circuit, the current is going to get higher and higher through the fuse, and the fuse is going to get hotter and hotter. Okay, it's getting hotter and hotter. So, and then at some point, when I connect the last one to the circuit, so it's going to be the current is going to be too large for the fuse. The fuse is going to melt. It's going to break the whole circuit. Okay, so you're going to see all these light bulbs go out. Okay, so that's the idea. Okay, so let's do this. So I'm going to first connect this to the source. Now this guy is already connected. Okay, so the current is not that large, so the fuse is still good. Okay, now I'm gonna screw this in. Okay, okay, still good. Okay, connected. The current gets a little bit larger, but still good. Okay, now I'm gonna do this. Hope you can see that in the video. Okay, I think this is very bright. Okay, and then it's still good. Okay, the current gets a little bit higher. Now let's do this. See if it can still take the whole current. Oh, still good. Okay, so now it's getting red. Now I can see that it's turning red. So it's really warm now, but I don't think you can see that because it's too thin. Okay, but once I try to connect this big one to the circuit, the current is going to be too large for the fuse. It's going to melt. So everything is going to go out. So be prepared for that. Wow. Okay, never gets old. Okay. So this is so cool, right? Everything goes out because the fuse protects the circuit from overloading if the current. But again, the disadvantage is that you're going to replace the fuse, right? So that's why now we use circuit breakers instead of fuse in a lot of places. Okay. So that's that. Now, okay, so we've finished that. Now, what we're going to do is that we're going to learn some two new rules to help us analyze very complicated circuits. Okay. So we have seen that if I use the theory for parallel and series circuits, right, I can always simplify a circuit, right, from like a lot of resistors to the final one with only one equivalent, right. Well, when the circuit is really complicated, has like a lot of resistors, I would have to draw all these diagrams, right? It's tedious, right? And then if I want to find the current, voltage, or power, or anything on a single element, I would have to use the diagrams to go backwards, right? To find all the numbers very carefully, okay? In order to find the element, the information of one element. So again, as I said, physicists always want to find like easy ways to do the algebra, to do the math. Sometimes there is an easy way, okay, so which is good. Sometimes there isn't. You just have to do the hard work. In this case, there is an easier way to analyze and more powerful way to analyze a circuit, okay, so which are called Kirchhoff's rules, okay. So these are very powerful rules. First of all, you can always use Kirchhoff's rules to find anything you need for every single element, like the current, voltage, or power, or anything, without drawing all these diagrams, without using parallel series theory, and it's going to definitely save you a lot of time, right? So that's good. And secondly, it's more powerful. It doesn't only apply to circuits with resistors. We're going to see that we can also apply Kirchhoff's rules with capacitors, or capacitors and resistors together, or even with capacitors, resistors, and inductors we're going to introduce later, okay? So they're very powerful rules. You can pretty much use Kirchhoff's rules to analyze any complicated circuits with any kinds of elements in the circuit. And also the circuit may have different voltage sources, right? For all these problems we have seen, we only had one battery in these circuits. We never had like more than one battery, right? Because we don't know how to combine batteries actually, okay? If you have like more than one battery in this circuit, how do you use this parallel series theory, okay, to simplify that. And how do you get rid of, replace these two batteries with one? We never learned how to do that, right? But in real life, the circuit may have some new, may have more than one voltage sources, okay? So using Kirchhoff's rules, you can also analyze a circuit with more than one voltage source, okay? So they're very, very powerful rules. So that's why we want to study these two rules, and then we're going to also use them later when we study inductors and then AC circuits with resistors, capacitors, and inductors. So that's our goal. All right. So what are these rules? Okay. There are two rules. So they're called junction rule and loop rule. Okay. The junction rule is this: the total current into a junction must equal the total current leaving a junction. Okay. And the loop rule is that the sum of the potential differences, which is just voltages, around any closed loop must be always zero. So they seem really simple, but they're really, really powerful, okay? You can use just these two rules repeatedly, very complicated, to find things you need, okay? So, and we're gonna continue this discussion next time. We're gonna see a real example, okay? Next time, I'm gonna stop here for this video.